The goal of this assessment project is to help you gain a deeper understanding of how the geometry of a molecule affects the polarity of that molecule. Let's look at the bonds that make up a molecule. One way that atoms form bonds with one another is by sharing electrons between atoms. This sharing can be fairly equal or very unequal depending upon the electronegativity of the individual atoms. The electronegativity of an atom is the relative measure of the atom's pull of electrons to itself. You can see that in the electronegativity chart. The more electronegative an atom, the more that atom will pull electrons to itself and away from other atoms that it is bonded to. Determining the polarity across a binary molecule, that is a molecule with only two atoms, is fairly straightforward. If there is a significant difference in the electronegativities of the two atoms, then the electron will be pulled toward the more electronegative atom, resulting in a partial negative charge on that atom, and away from the less electronegative atom, resulting in a partial positive charge on that atom. This unequal sharing of electrons between the two atoms results in a separation of charge across the molecule. That separation causes the molecule to have a polarity in charge. This is very similar to the poles in a magnet. Thus, this particular molecule with the separation of charge is considered polar. If there is no separation of charge, like on top here, then the molecule is considered nonpolar. Let's look at two examples of binary molecules, H2 and HF. I will be using models in this video where the atom size reflects its electronegativity. That is, the more electronegative the atom, the larger the model atom. In our first example, H2, which is on the top here, they have the same atom, hydrogen. So they have the same electronegativities, 2.1 from your electronegativity chart. In the model, the atoms are the same size. Because the electronegativities are the same, the electrons will be shared equally in that bond. As a result, we don't see any separation of charge across the molecule. As you can probably guess, H2 is considered a non-polar molecule. In our second example, however, hydrogen monofluoride, down here on the bottom, the hydrogen has an electronegativity of 2.1, which we saw before. But the fluorine atom has electronegativity of 4.0, which is almost twice that of the hydrogen. As you can see in the model, the fluorine atom is represented as much bigger, representing a greater electronegativity. It also shows that the electrons will be pulled more towards the fluorine and less towards the hydrogen. Here it seems pretty straightforward that the fluorine atom pulls the electrons that create the bond towards itself and away from the hydrogen. This results in the fluorine having the partial negative charge and the hydrogen having a partial positive charge, thus a separation of charge. As a result, HF, or hydrogen monofluoride, would be considered a polar molecule. So far, so good. But these are simple examples. What happens when the geometry is not that simple? When you have, say, 3 or more atoms? Well, next let's look at molecules with 3 atoms. Now let's look at our 3-atom molecules. Again, we will look at 2 examples, sulfur dioxide, SO2, and silicon dioxide, SiO2. If we only look at the differences in electronegativities, if we look at sulfur with 2.5 and oxygen at 3.5, and then at silicon at 1.8 and oxygen at 3.5, you might guess that both molecules are polar. But does their molecular geometry actually play a role? Well, with our first example, sulfur dioxide, which is here on the bottom, it has a bent geometry, meaning these oxygen atoms are bonded to the sulfur atom at angles to each other. As we can see in the model, the more electronegative oxygens are bent towards one side of the molecule, creating electrons to be concentrated on that one side. Thus, there's a partial negative charge on one side of the molecule and a partial positive charge on the other side of the molecule, a separation of charge. Therefore, this molecule, sulfur dioxide, is considered polar. In our second example, however, you'll notice there's a different geometry. It's up at the top. Silicon dioxide has a linear geometry, meaning all three atoms lie on one line. From the model, the more electronegative oxygens do not create a partially negative side as they did with sulfur dioxide. Instead, the electrons are pulled 180 degrees from one another. This does not create a separation of charge. The charge is basically distributed across the whole line. Therefore, silicon dioxide, SiO2, is nonpolar, even though the individual bonds between silicon and oxygen are polar bonds. The molecule as a whole is not polar. Now your assignment is to look at molecules with 5 atoms, starting with methane, CH4, which I'm showing you here. This exercise requires you to think in 3 dimensions. You will also assess, based on electronegativities of the atoms and their geometry within the molecule, whether each molecule as a whole is polar or nonpolar, and why you think that. Then you will make a series of substitutions for each hydrogen bonded to the carbon. You will look at a total of 5 molecules in all, starting with methane, and then your final atom will be carbon tetrachloride, which will have all of the hydrogens substituted with chlorines. Read through and possibly print out the assessment exercise document. A copy of the electronegativity chart is included in the assessment document as well. To recap, you will first complete a pre-assessment questionnaire on the 5 molecules to evaluate your initial knowledge and assumptions. Next, you will complete the assessment exercise. That's the one in PHET. Answering similar questions in your post-assessment questionnaire. These are on the same 5 molecules. Answer these questions at the end of the exercise. They will also be listed in the post-assessment exercise document. What happens to the polarity of a nonpolar molecule if you make a substitution for one of the atoms? Can that substitution affect the polarity? Does the molecular geometry make a difference? Can molecules with polar bonds be, in fact, a nonpolar molecule? Thank you.